Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I think we'll get started. Jay will probably get started. So it's my great pleasure to introduce Haryati Gunawi. He has done great work in a wide variety of forums in SOSP and OSGI and FAST and ISCA, giving us a deep understanding of the way storage systems propagate and handle failures in both hardware and software. So today he's going to be telling us about how we can create more reliable storage systems. So thank you.
All right, thanks, Ed. And thank you all for coming. So today I'm going to talk about my research contributions towards building more reliable storage systems. So again, just like Ed says, my research is about file systems, which is an important piece of the operating systems. And if you look at years of file system research, basically we'll find many innovations in many different aspects. For example, people try to improve performance by improving allocation policies, improving write performance, and many other aspects. Functionality has also received a great deal of attention. People try to make the file system scalable so that we can store millions of files. People try to incorporate search interface within the file system so that we can easily search our files. Well, other than that, reliability has also been a focus simply because the hardware fails and no one wants to lose their data. So what I want to focus in this talk is to focus on the reliability aspects of the file systems. Okay? So since my research is about reliability, here's the roadmap of my reliability research. So my research was driven from this unfortunate reality that storage systems still fail today, and the failures that arise are quite diverse, as we'll see soon. And the file system needs to manage all these kind of failures. So the first questions that I ask is, how do we know that today file systems are doing a good job in dealing with storage failures? So the first part of my research is to measure the reliability of today file systems in dealing with storage failures. Turns out what I found is that in today's file systems, the failure management is very complex, which leads to many problems that I will show you later. Okay? So given this another unfortunate reality, the second part of my research is to build more reliable file systems that can deal with storage failures in a better way. Okay? And in order to do that, I will adhere to the principle that complexity is the enemy of reliability. So my hope is to bring today's file systems and so that we can build tomorrow file systems that are powerful, reliable, but with simplicity in its design. Okay. So given such a roadmap, here are my contributions in a more concrete way. So since this is a file system research, there are two important components that I have looked at. The first one is this offline file system checkers, or in short FSCK, and the second one is the file system itself. So when we talk about FSCK, this is a very important utility that should repair any damage in our file systems and bring your file system to a consistent and usable state. But when I measure the reliability of today's file system checkers, I found they are not really reliable. I found that some repairs are missing, and some repairs are actually incorrect, such that the resulting file systems become unusable because they bring more damage to your file systems. Okay? And I believe the reason why this problem exists is because of the complex implementations of today's checkers. All checkers that I know of are still written in this low-level C code language, which is hard to reason about. Okay? So to improve these situations, I will introduce you to the idea of SQCK, which is a robust file system checker that uses a declarative query language, such as SQL, so that we can write hundreds of check and repairs in a much more clear and compact manner. Now, when we look at the file system itself, again, it turns out that today file systems are not really reliable because some storage failures are being ignored, and the existing policies are inflexible. They are very hard to change. So if you want to add new policies, it's just hard to do in today's file systems. And I believe the problems exist because of the reliability code that deals with storage failure in today's file system is very scattered, and there's no good abstractions in dealing with storage failure. So in order to improve these situations, I will introduce you to the idea of shepherding, which is a novel reliability layer where we can deploy centralized, flexible, and powerful policies. Okay. And again, in providing the solutions, my principle is about simplicity. All right, so here's the outline of my talk. So in the next section, I'm going to give kind of a little background of my research. Why are we still doing reliability research, although file systems have been out there for more than 2 decades? Okay? And I'll show you how storage subsystem fails today. And then I'll move on to my two major contributions, which is improving the constructions of file system checkers with SQCK and simplifying reliability management with shepherding. And for the rest of the time, I'm just going to briefly describe my research in other disciplinary areas such as software engineering, databases, distributed systems, and networking. And then I'll close with future work and conclusion. All right, so why are still we doing kind of reliability research? Because I believe the failure models, that there are new failure models that haven't been looked at really kind of in more details. But if you look at the old fault models, there are two fault models that have been pretty much solved today. The first one is to anticipate whole system crash. And the whole idea, people realize that the whole system can crash, and that's not good for a file system because file system performs multiple updates. And if a crash happens in the middle, you can have inconsistency on the disk. Okay? So basically, file system researchers borrowed the idea of logging and journaling so that we can perform atomic updates to the disk. The second fault model is to anticipate whole disk failures. Again, people realize that the whole disk can be lost, and if that's the case, then our data can be lost permanently. And so Patterson, Gibson et al. Basically suggested the idea, let's just have more disks, and if we have more disks, we can do a simple mirroring like this. Or to reduce the space overhead, what we can do a parity scheme. But the whole point that if a disk is lost, we can still reconstruct the data. Okay? But we'll see that today modern storage failures are much more diverse beyond whole system crash and whole disk failures. And so the model of failure has changed a little bit, and I'll show you why. The reason is because what's underneath the file systems is not just a simple disk, but it's a stack of complex components. We have device driver, we have the controller, we have the firmware, electrical mechanical components, and media. Now the point is that all these components are not always reliable. People have seen how each of these components can fail in practice. So basically my point is that from the file system perspective, there's a broad range of failures that can arise. Not only we have whole disk failures, but we also have partial failures where some blocks on the disk become inaccessible. Sometimes we have intermittent faults, sometimes we have permanent faults, and sometimes we have this kind of crazy failure modes where the writes are suddenly misdirected, torn, or lost. Okay? So over the time, because all this problem, our data can be lost and corrupted. Now, if you wonder how these failures happen in practice, yes.
So I couldn't follow. Why are these new failures? That's why I mean.
Right.
You're saying these failures didn't exist before.
Yeah, it exists before, but in the community they consider this as anecdotes. It's like they don't believe that this failure happens unless.
It's not that the failures are new. It's that the community hasn't looked.
Yep. So
You just said that the failures are new.
Right. I guess new in the sense that we need to look at this kind of failure modes that we haven't looked before. So I guess new in that kind of sense. Right. Okay.
The other thing happens, these are fairly low rate failures, but as you get bigger and bigger storage systems, the chance that they're occurring gets larger.
So, as I understand it, much of what you said applies to disk, but nowadays there are solid-state drives and flash is starting to replace disks in many computing environments. Can you say a few words about the...
Yeah, good point. Well, first is that I don't think many people have looked into the reliability aspects of flash devices. That's the first thing. And if you look at, again, the storage subsystems, is that when we look at the flash drive, it's just the kind of lower level component that has been changed. But in the middle, you will have kind of this device driver for drives, right? And when kind of these flash drives are becoming more popular, usually the device driver will be much complex in dealing with any kind of things within the device. So when we talk about file systems, it needs to deal with all the things that are happening underneath this, not just the kind of the media stuff.
So what you're going to present is going to be possibly applicable to flash as well.
Yep, I believe so. Thank you. Right. So as you can see, these failures happen in practice, and I want just to focus on the last two, which is a large-scale study done by my colleague and the people from the storage industry, in this case, Network Appliance. So they study 1.5 million drives that they kind of sell to their customer, and within this population, 4% of the drive exhibit latent sector errors, where some part of the disk become inaccessible. And among this population, they found 400,000 blocks have been corrupted. So these blocks can return to the file systems, but the content has been corrupted. Okay. All right, and this is not about storage subsystems that we use in the daily basis. This is kind of still $1 million storage systems that they sell to the customer, but they still see this kind of failures. Okay, so the whole point is that storage subsystems fails in a diverse way, and what we look again is how today offline file system checkers should kind of repair any inconsistency or any damage in your file systems, and we'll also look at the file system component part, which is a part of the operating systems, in how they deal with storage failures. And again, although my research has been within these core operating systems, I believe the principle and the techniques can be extended to other research areas, from personal devices to kind of a large-scale cloud computing as well. Yes, Ed?
Why doesn't journaling obviate the need for an offline checker, since it's applying atomic updates and it has a recovery model?
Right, because over the time your data can be corrupted not because of crash. Right, sometimes your media just worn out, or sometimes you have a head crash, so it scratches a portion of your disk, so you will lose some part of your disk, and so in that case your file system looks inconsistent. Right? So for example, your middle directory might be lost, so you will lose access to all kind of the lower directories. So you need file system checkers to repair everything. Okay. All right, so let's look on to my first contributions, which is Squeak. So what I'm going to show you is the problems that I found today in Today Offline File System Checkers. And of course, the solution after that is with Squeak, how we can simplify the constructions of file system checkers. And then let's evaluate Squeak. Okay. So before showing you the problems we found, let me just briefly describe the file system data structures. So in this case, I take ext2 file system. So if we have an ext2 file system, it always starts with the super block that has rich information about the layout of the file systems. So ext2 file system is divided into groups. Its group is described by a group descriptor block. So its group descriptor block has information about the locations of inode table. And inode table is just basically an array of inodes. So an inode can represent a file, or it can also represent a directory. And an inode basically has pointers to the data blocks. So if the inode represents a file, then the data block is your user's file, is your data. But if the inode is a directory, basically data blocks contains directory entries. Okay? And if the directory is large or the file is large, the inode points to an indirect block, which eventually points to data blocks. Okay? Now, when we talk about storage failures, that can be like sector errors, where some blocks become inaccessible. So if you do not replicate your inodes, then you might lose some of your directories or files. If you do not replicate the indirect block, for example, you might lose all the pointers to the data block. Okay? So this is kind of the failures that the file systems needs to handle. Well, other than that, corruption can also occur. For example, the inode has kind of pointer to the locations of data in an indirect block. That pointer can be corrupted. For example, suddenly it points to super block. Okay? And the kind of file system checkers needs to catch this kind of corruptions and fix that. Okay? All right, so let's see the reliability of today's file system checkers. In this case, I analyzed the ext2 file system checker. So the task of E2-FSCK is just, and a typical FSCK basically is just to cross-check all the internal metadata, find any inconsistency, and repair that inconsistency. Okay? So for example, for ext2, it needs to check that an indirect pointer should not point to the super block, because indirect pointer should point to an indirect block. It should also check that a subdirectory should only be accessible from one directory. And basically, in today E2-FSCK, it needs to do a total of 150 cross-checks. Okay? So in order to understand the reliability of today E2-FSCK, basically I injected single corruption at a time. And we want to see how E2-FSCK fixes the corruption, how it repairs the corruption. Okay? So I'm going to show you two examples of kind of this fault injection. The first example, that I corrupted an indirect pointer such that it points to superblock, and we'll see how E2-FSCK repairs this. And the second example, I corrupt a directory entry such that it points to another directory. So let's see the first example. So here's one problem that I found in today E2-FSCK. This is a problem of inconsistent repair. What I mean by this is that the resulting file systems actually become more inconsistent and become more unusable. Okay, so that's why inconsistent. And the reason is because the out-of-order repair that we will see soon. So what I'm going to show you here first is that what an ideal FSCK should do. So let's say we have an inode, and inode has this indirect pointer, and the indirect pointer is corrupted such that it points to the superblock. What you want to do is to check the validity of the pointer, right? And since this is a corrupt pointer, we want to clear that pointer such that it points to nothing. But if the pointer is correct, what we want to do next is to check the content of the block that it is pointing to. For this indirect block, the check that we want to do is we scan its entry. So its entry is basically the locations of the actual data blocks. And for its entry, we want to find locations that fall outside the file system range. So let's say if the third entry looks corrupt, it will kind of fix that entry to 0. Okay, so that's what an ideal FSCK should do. Let's see what E2-FSCK does. So what E2-FSCK does, this is the whole idea of out-of-order repair, because it assumes that the super block is an indirect block. So it assumes that the indirect pointer is correct. So in that case, it will try to check the content of the indirect block, which is actually a super block. And since the super block doesn't look like a healthy indirect block, of course, obviously, it accidentally clears some of the fields in the super block. And later, it checks the validity of the pointer, and oops, turns out that the indirect pointer doesn't point to indirect block, and it will clears that. But as you can see, the super block has been corrupted. It's too late. Okay? So there is one problem that we call out of order repair. Let me show you the second. Yes?
So what is the goal of the repair here? Is it to create a usable file system or to restore the contents to?
Yeah, two goals. Usable, and the second thing is to repair the file system to match the original file system to the greatest extent possible. And I'll show you in this second example here, the resulting file system is usable, but it doesn't match the original file systems to the greatest extent possible. Okay?
So format would also meet that test.
I'm sorry?
Format, if I reformat the volume, I end up with a consistent file.
Right, but it doesn't. Right.
That's the first test. It doesn't really do very well.
Doesn't match the second.
Yeah, thanks for bringing that up. So here another example of incorrect repair. So I'll show you what an ideal FSCK should do. So let's say we have a directory A1. A1 has a subdirectory A2. We have a directory B1, and B1 has a subdirectory B2. And let's say we have a corruption such that the directory entry in A1 suddenly points to B2. Right? Well, fortunately, in the ext2 file systems, for its directory, we maintain a backward pointer to its actual parent. So everyone can know the true parent-child relationship, which is B1 and B2, and then we can identify the corrupt pointer, and A2 will be put in lost and found. Okay? So that's what an ideal FSCK should do. Yeah, but you cannot. The whole idea is that what kind of pointers that you trust. Since A2 is just one pointer pointing to A1, and A1 doesn't claim that A2 is his child. So, I mean, in today U2 FSCK, you cannot claim that that's the true parent-child relationship. Okay?
Could you clarify what lost and found is?
Lost and found is just a directory underneath the root directory. So if there is any directory or any file that is not reachable from the root directory when the offline FSCK is run, those files and directories will be put inside the lost and found directory. Okay. All right. So what happens in E2 FSCK is brutal because it selects A1 as the actual parent because coincidentally A1 has a lower inode number than B1. So although B2 claims that B1 is its actual parent, E2 FSCK doesn't care. It forces B2 to accept A1 as the actual parent, and B1 is just a sad parent because it just lost his kid. Okay. And so this is pretty much kidnapping problem that happens in E2 FSCK. But the whole point is that E2 FSCK does not use all available information to perform correct repair. Yes, Jeremy.
Do you have any sense for how common these sorts of failures are in the wild?
Good. Oh, well, we don't have kind of statistical failure at kind of this granularity at a high level. But as an offline file system checkers, you need to handle the worst case of failure. Right? This is kind of obvious case that you should not perform a repair like this because you have enough information that where you can kind of repair things correctly. All right, so as a summary of problems, you have seen the first two, which is inconsistent repair, and again, consistent but not correct repair because the resulting file system doesn't match the original file systems to the greatest extent possible, and also other problems that I'll have to talk about this offline. But the whole point is that when we have these problems, what we can say is just let's fix this problem, right? Let's just eliminate this problem. But if you want to do that in the current framework, that won't be so easy. And in fact, one FSCK developer has admitted the same thing to me. We might introduce more problems. And the reason for that is because the complex implementations of today file system checkers. All checkers that I know of are still written in this low-level C code language, which is hard to reason about. So as a result, the resulting implementation is large and complex. For example, ext2 FSCK needs to do like 150 checks in 16,000 lines of code, while the ext2 file system itself is kind of less than 10,000 lines of code. XFS FSCK needs to do 340 checks in 22,000 lines of code. And if you look at the code, it's just basically hundreds of clouded if check statements. Okay? And there are several bad implications. It's difficult to combine available information on the disk to perform correct repairs. It's difficult to ensure correct ordering of repairs. Basically, it's hard to find missing checks or incorrect checks in this current framework because of the clouded code. Okay?
Is there some reason that FSCK is a harder piece of code to write than because 16,000 lines of code is not substantial. Right? NTFS is 350,000 lines of code, and it almost sometimes works. right? So is there some particular reason to believe that FSCK is harder than other?
Right, so what I'll show you is that the basic test of FSCK needs to do hundreds of cross-check. That's what it needs to do essentially, right? But in terms of the implementation, what I'll show you is we do not need to implement things in C code, which is basically what happens in today for some checkers. It clutters all the kind of data traversal, all kind of loading the data and cross-checking, right? So basically, I'll provide a better framework for doing this.
I think he's asking is there something fundamental about checking a file system that makes it more difficult to reason about in building the file system itself?
Yeah, well, in a sense, I believe yes, because it needs to find any inconsistency, right? And for its inconsistency, sometimes you want to do a certain kind of repair. That's why when people ask me why don't I write like a modeling language that kind of tell what's the truth about the file systems. The problem is that even if I use modeling language, usually it's hard to express the repair. Usually what FSCK does is to find inconsistency, and for that specific inconsistency, you want to do a specific repair. So that's where the hard part. It needs to find any possible damage in your file systems. Yes.
So do you assume that the original file system code is non-buggy? And all these errors are caused by...
Oh, no. I mean, for file system checkers, you need to anticipate that the file system code can be buggy, which leads to basically at the end what you have is inconsistency on the disk, right?
So in a way, it's like you're specifying, you have two specifications, right? One is the file system code itself, which implements the specification, and then the checker, which implements a different spec of the same file system. So do you check whether these two match, or...?
No, I haven't really explored that one, but it will be an interesting stuff to do. All right, so bottom line, what happened? Yep.
Is that possible? Have you thought about formulating this problem as an optimization problem? Because you're kind of trying to recover some pointers from a node to another node. I'll say recover some edges in a graph given all the vertices. And you can look at the whole thing globally and try to find something optimized globally.
Yeah, I think that's a good point. I haven't explored that. And well, I believe with my framework that I'll show later, it's probably easier to do that because all the checks are kind of basically sequenced kind of in a better way than kind of cluttered code. Yep. Okay. So bottom line, what happens out there is that this FSCK code is untouchable because this is a very crucial recovery code, but it's so hard to fix. If you fix this and you introduce more problems, then you're in a bad shape. Okay. So obviously we need a new solution. So I'll talk about SQCK, the architectures, and how we can write simple checkers. So the whole point is we need to build a better file system checker framework. And again, the point here is that the original task of FSCK is already complex because it needs to cross-check many stuff, and we do not want to combine it with another ad hoc designs which will lead to complexity and unreliability. Okay? So the lesson is that complexity is the enemy of reliability. I want to simplify the framework without losing any power or sacrificing any performance. So the whole idea with SQCK is a robust file system checkers that uses a declarative query language as a SQL so that we can write hundreds of checks and repairs in a very clear and compact manner. The whole point, if you look at the nature of a check, is just please find an inconsistency on my file systems. And if you look at the nature of a query, pretty much the same thing. Please find something in the database. Yep.
Are you assuming you can't make any changes to the file system to add additional information as it's being generated to help you later in FSCK?
Well, okay, so no, you can do that because when you do, I'll show you how we can use SQCK. Basically, first we load file system metadata to the database tables. So during that particular, I will tell you more in the next slide. Okay. All right. Thanks. All right, so there are lots of benefits. Again, the high-level intent of the checks can be clearly specified, as I will show you soon. Basically, what you care is just you write fewer lines of code. And basically, it's easy to cross-check and repair massive amount of information because that's what a SQL query language was built kind of from day one to do. Okay. All right, so let's see how we can use SQCK. We take file system image, and basically, we load file system metadata to the database tables. And if you want to add information while you're reading the image to help the checks, you can do this in this particular phase. Okay. And then the whole point is that since all informations that we want to cross-check and repair resides in the database tables, we just write all these checks and repairs in a declarative manner with the query language. Okay. And if there's any modifications, we'll flush that modifications to the file system image so that the resulting file system is consistent. Yes.
So is this going to be an in-memory database?
Yeah, this is an in-memory database. Well, so far what we have I haven't really looked into the implementations if we need a backup storage, how we're going to do that. But even in today's file system checker, let's E2FSCK, for example, if the memory doesn't fit, the E2FSCK developer says that it cannot run. So I think that's kind of another design issues when we're designing file system checkers. Good point. Sorry?
Right. You can't have a serious file system that has the property that you can't run FSCK on it if it's got enough files that its metadata doesn't fit memory.
Yeah, so that's why I mean in today to FSCK, what they do is sometimes they build the summary, and then if the summary, they find inconsistency in the summary, they'll read the metadata again, right? So again, that's another design issues. Well, for me, it will be, since we just run a database, and as long as the database can use a backup storage, there'll be just, I believe it's just another installation of backup storage for this case, okay? But
Storage that you can safely write to while you have an inconsistent file system.
Yeah. So that's kind of the vulnerability, because when we run this, the storage itself might be broken for that particular time.
That's something that you cared about.
I'm sorry?
You might find out that your database just overwrote something that you cared about, but you didn't know because the file system was inconsistent when you tried to USB stick.
He did say
Yeah,
backup.
you can do that.
Yeah.
Or using the disk.
Okay. All right, so in the next couple of slides, I'm going to show you how we can write simple checks with this SQCK. Yes?
So presumably the scanner and the loader is pretty simple, right? It's pretty straightforward.
Yep.
Because if one of your enemies is complexity and who knows what's going on in the file system, then you'd hope that step is very simple.
Yep.
Right?
Mm-hmm.
So is that true?
Yeah, that's true. That's very true. Yeah. If you know the file system structures, you just read the file system structures. And when I compare SQCK with the original FSCK, I only compare this part. I do not compare the loading, the scanner part, because it's very easy. There's not much complex logic there. All right, so here's how we can write simple checks. So this is one check that E2FSCK needs to do. It needs to find block bitmap that is not located within its block group. This is a very simple range checking. And here's what you get with E2FSCK. The core logic of the check is hidden in this implementation details. But here's what you get with SQCK. It's very simple. The query will just return block bitmap that does not reside within the start block and end block group. Okay? I'm going to show you a little bit more complex example. This is, again, the idea of we're trying to find the false parents, which are directory entries that point to a subdirectory that already belongs to another parent. So in this case, we need to cross-check all directory entries. And as a note, this is wrongly implemented in E2FSCK, which leads to the kidnapping problem. So here's what you get in E2FSCK. Well, no one will understand this code unless you write this code. And anyway, this is the wrong implementation. Okay? So let's just throw this away, and I can introduce you to a new query which fixes the check. So we do have 3 simple selections. First, we scan all child pointers. So in this case, we kind of omit entry number 1 and 2, because entry number 1 and 2 is the dot and dot entry. Those 2 entries will be checked in another query. Basically, so after these first selections, we will have P saying that C is your child. And we'll do a second selection where we scan all parent pointers. So so we scan entry number 2, which is the dot dot entry. So after the second selections, we have C saying that P is its parent. So we can establish the true parent-child relationship here. And we also just do another third selection where we find F, which is not equal to P, but F also claims that C is its child, and we'll just return information about the false parents. Yes?
Sure. I mean, what's your notion of sort of code complexity here? Because it seems like there's still a lot of stuff on this slide, right, as compared to the other slide. And so is it that you're just expressing it in this SQL way, which you sort of you found in your experience is simpler to, because it still seems like you have a lot of conditionals and.
Right, but if you look, a check is basically expressed in this one simple query. Right? If you look at the original E2FSCK, if you want to find a particular check, you find a kind of cluttered C code, and you need to know where this data structure is being read before, where it's stored and everything like that. So the whole point, like the data traversal and the logic of the check is very cluttered. But in here, you don't care about the data traversal because the database community has done a great job for providing us SQL, right? Here you just express the logic of the check, and it will do the traversal by itself.
I'm just wondering how much of the gain you get from just refactoring the C code. I mean, if you just sat down and.
Right. In terms of the logic of the code, I'll show you later that we can write much fewer lines of code with SQL statement. Okay.
And it seems like via sort of, I don't know, maybe via lambda calculus, you could prove and things that sort of you don't have one test here that's almost undoing some other test in a way that I don't think you could do with writing it by hand in C.
Yeah.
I mean, as you go to, you said 340 checks for one file system.
Right.
I mean, how do I know that test 37 isn't undoing what test 97 just fixed?
Right. So there's another question: how do you check the checker? This is kind of larger design. Yeah. So what I've done is to simplify the framework, so that hopefully we can have a better world by verifying the checker rather than verifying the C code. Okay. All right. So let's evaluate SQCK. So I've evaluated SQCK in 4 axes of evaluation.
All you did so far is find problems. How do you fix them?
I'll show you. I've
okay.
fixed the fixed existing problems, and I even introduced new repairs.
Okay,
but
you were getting into evaluation already, and I didn't understand how you
flexibility
update.
and reliability. Okay, thanks for beginning. Okay, so 4 axes of evaluation: simplicity, reliability, flexibility, and performance. So in terms of simplicity, I have written E2FSCK in the form of 150 queries for a total of just 1,000 lines of code of SQL statements. And we need the C code to combine all the SQL, but the C code is very simple. You just combine all the SQL statements. But you can compare that with 16,000 lines of the original implementation in C code. And reliability, I don't claim that I have tested everything, but so far we have injected hundreds of corruption scenarios, and SQCK has passed all of them. But the point is that, again, if you find a check or repair is missing, you just add a query. If you find a check or repair is buggy, you just simply fix the query. Okay?
Lines of code were in the thing that parses and implements the SQL, or did you? I mean, you just used a real database.
MySQL. I just used MySQL. Yeah.
So I don't know too much about this area, but you said that you injected several different faults or failure sort of, examples into the file system, and you were able to catch them. But I don't find that surprising, since it's you who wrote the tests.
Yeah, that's why I mentioned that I don't claim that I have 100% coverage. What I've done is I injected these 100 corruption scenarios, and if I found that my checker doesn't fix that, I'll add a query. But I agree with you that the whole point is that there will be another issue of how we can generate like a 100% coverage to test any corruptions in my file systems. But my point is that the point is in this 2 bullet point is that if you find that you have a missing repairs or missing checks, you just add a query. You do not need to add code in E2FSCK like in C code.
So were there any problems that your implementation discovered that the original C code could not detect?
Yeah, I'll show you later. There are some kind of checks that are missing. Okay.
So I had a related question to that. So you said one of your goals was to also detect bugs in the operating system code when it tries to leave the file system in a corrupted state. So why not inject faults in the file system code and then see if you're able to fix them?
Right. I mean, that kind of relates to the testing part. I haven't really kind of done that, but I mean it can be doable basically. But I mean the whole point is that the bugs in the file system code, I mean you can see that as kind of corruptions underneath the storage. At the end, from the file FSCK perspective, is that the file system is inconsistent. So you need to find any inconsistency in the file systems and repairs that.
But that would be a founder test of your...
Right, I agree. Yeah, so that will be kind of in this testing world that I haven't fully explored. Yeah. Yes?
Can you give us some intuition for how many times it took you to get things right? So the real question of the expressiveness of the language is, if you hadn't had this test infrastructure to keep running to getting it right, how many times would you have gotten it wrong?
Well, this research was done 3 months before the OSDI deadline. So 2 months before that, I borrowed a MySQL book from the library. So that shows you how we can, but I cannot tell that to the program committee. But that's the kind of the whole point, how we can simplify things with this query. Does that?
For number of iterations that when you went through to check, did I get all my corruptions?
Oh, yeah.
Did you get them the first time? Did it take 2?
Yeah, you take 2, 3 iterations, but you just focus on this very one kind of localized query, right? You do not need to handle other logics. It's not cluttered, basically.
So is it 90% of the time you got it right the first time?
Depends on the cross check. I mean, I don't have the slide, but there are cross checks that you must done with multiple instances of multiple different structures. So for that particular cross check, it's hard. But there are some cross check where you can do with across some fields within one structure, and that's simple. You can do one iteration and you get it right. So depending on the type of the cross-check that you do. Okay.
If some corruption scenario is not being handled, is it trivial to figure out which query to fix? Or like there are 150 queries, so is it trivial?
Right, so the next thing is what you can do is you can, again, the whole idea is go back to how do you check the checker, right? It would be nice to have a formal model of what the checker should do and compare the formal model to the sequence of the query that I run.
In my mind, it was like, I mean, you have 150 queries and you see some corruption is not being fixed. And how do you go back from that observation to which actual query should you fix?
So the checker, basically, the model is divided into phases. Okay. So in the first phase, for example, you check the super block, you check the group descriptor block. So pretty much just a very minimal structures that you check. So if your corruption basically kind of deals with those few structures, then you do it in the first phases. But if your corruptions relate to like a link count or different more complex checks, usually you do that in different phases. Right? So you must get the sense of what the phases are within today's false system checkers, and if you find a corruption that relates to a certain phase, you try to look at the queries for that particular phase. Does that answer?
What's the most complicated query in the 150? Like how many blocks or inodes this query has to check? Because the example you show like three of them, right? A1, B1, B2. You only need to check three. What's the most complicated query? Blocks or inodes you need to check?
Yeah, well, that one is actually, I mean, if you look at the SQL, it's complex, but turns out if you look at the query, it's not that complex. Sometimes you do like complex cross-checks like link count, but the point is that you need, the complex cross-check is cross-check that you must do across multiple structures and across many multiple instances of
MySQL anyway, right? I mean, when you write the query,
since he's only halfway through his talk, can we wait a little bit and let him move forward?
Okay. Okay, so in terms of flexibility, the point is that I've improved E2F by fixing the wrong repairs and adding new repairs. So these are the type of repairs that you cannot find in today E2F, but the whole takeaway point is that you can add these new repairs in a very few lines of code. Okay? And performance, just quickly here. So we compare Squeak and E2F in 4 different file systems with different sizes. Its file system is half full. The y-axis shows the total runtime normalized to E2F. So here's E2F time in terms of seconds. And here's Squeak time normalized to E2F. So, but the whole point is that Squeak stays within the 1.5 times the original E2F performance. And I believe there are many optimizations that we can introduce. Right, so for this one, we have like 300,000 files, mixed small files, large files. Okay. All right, so what we have looked is this idea that problems in today's file checkers and how we can have a better world with Squeak. So I'm going to move on to the file system part. So again, I'm going to show you the problems today in file system checkers, and I'm just a co-author for this particular paper. It was led by Vijay Prabhakaran, who is a researcher at Microsoft Silicon Valley. But I'm going to solve these problems with IO shepherding, and then we can evaluate IO shepherding. Okay? So let's see the problems that we found together with Vijay and other colleagues here. So here, basically, we measure ext3 reliability. And the way we do that is we inject read and write faults of different block types. And when we inject these faults, we run different file system operations. Okay, so the result that I'm going to show you is basically in today's file systems, we have this problem of inconsistent, incomplete, scattered, and inflexible policies. And I'll show you the progression, how we can come up with this conclusion. Okay, so basically, we want to measure the reliability of read recovery policies. So we run a bunch of workload, open, read, write, and so on. And when we run this workload, we inject read failures on different block types. Okay, so and basically all the gray boxes means unapplicable experiments, and we found 4 recovery strategies in ext3 read recovery policies. So let's just take one simple box here. So for this particular experiment, what we did is we run a path traversal workload like CD and the path, and during this path traversal workload, we injected read failures on the indirect block. And what the policy that we observe is that the failure is detected and it's propagated to the application. So we mark this with kind of horizontal bar, which means propagate. Okay. But the takeaway point here, you can just focus on this red area. For the same read failure on the indirect block, the ext3 file systems takes different recovery responses. Sometimes it propagates, sometimes it retries the operation, sometimes it ignores the failure, and sometimes stops the file systems. Okay, so that's how we can conclude that it's inconsistent. And this is the write recovery policies. And just quickly, you can just focus on all these circles. It means that all write failures happening when you run this workload and all the write failures happening on these block types are being ignored by the file systems. So if this happens in your case, then your data or your file will be lost suddenly. Okay, so this is what I call incomplete policies. Okay, so basically how should we deal with storage failures? Well, there are lots of techniques out there. And it has performance and reliability trade-off. The point here that I want to make is sometimes what you want to do is you want to deploy a particular set of policies. Let's say you want to add mirroring and checksums in ext3. Okay? So the same principle, we can just do that. And what I'm going to show you is that if we do that in the current framework, it's not so easy. And the reason for that is because of scattered reliability code in ext3 file systems. Okay? So the x-axis shows the source files in ext3, and the y-axis shows the line number that shows the storage failure management in these file systems. So as you can see, basically there are hundreds of places. So when I want to introduce new policies in these file systems, you must do it like everywhere. So that's why I claim this it's inflexible.
Clarification question. What do you mean by reliability code?
Right. Well, basically the file system needs to handle read failures, write failures, right? And the file system do that in many different locations. And what the file system tries to do is to handle its fault in its I/O location. So that's why everything is scattered. Does that answer your question? It's basically handling read and write faults of different block types. Okay, so we have this problem, and it's not only happening in ext3, but also RiserFS, IBM JFS. When I talk informally to people in the storage industry, they may also mention that these million-dollar proprietary file systems also have the same problems, but of course, we cannot really say much about that. So it means that we need a new reliability framework in dealing with storage failures. Okay? So I'm going to show you the idea of shepherding, the goals in architecture. So the whole point with the shepherd is this is a nice layer underneath the file system. It's pretty much integrated to the file systems, where it locally takes care of the reliability of the I/O requests. So the file systems will send read and writes, and it will be interposed by the shepherd. And we'll see later how we can add reliability within the shepherd. So there are three important goals. The first one is that, as you can see, the original policies are very much like scattered throughout the file system code. What we want to do is we want to localize everything within the shepherd. Okay? Because the whole idea that with localized policies, we can have more correct, less buggy, and much more simple reliability management. And probably you can do verifications within that layer too. The second thing is, since everything is localized, it's very easy to achieve flexibility. Okay? We can deploy different kind of policies for different environments or requirements. For example, you might want to add mirroring to protect archival volume, or you want to add checksum to protect corruptions of scientific data. But the whole point is that different policies for different requirements or environments. Okay? And the third goal is that we can combine one of more these basic policies to form more powerful policies. Okay, so to achieve this, yes?
What layer the shepherd is at? Does it think about blocks? Does it think at a
blocks.
high level?
Blocks, yeah. But it's pretty much integrated with the file system, because sometimes what you want to do within the shepherd is to understand the block types within the file systems. So you need to understand the ext3 block types. If you want to deploy shepherding for Windows NTFS, for example, you need to know the Windows NTFS block types within the shepherd. Yeah.
So how does the low-level subsystem know whether it's archival or scientific data, or are you assuming?
Assume file system administrators. Yeah. So basically, I assume that the file system administrators who will write this kind of policies. I mean, so far, when we have file systems, usually is the policies that the file system developers writes, right? And file system administrators needs to understand the file system kernel code in order to change the policy. But the point is that the hope within the shepherding layer, we allow file system administrators to compose different policies, because everything will be simple in this layer. All right, so to achieve that goals, I'm going to describe a little bit about the four important components in the iShepherd: the policy table, policy code, primitives, and policy metadata. Okay. So basically, we want to build a new reliability framework in file systems. So we asked the first question is, how do we specify reliability policies? Because we do not want to introduce another ad hoc solution. So basically, I come up with these two different facts. The first fact is that usually file systems has different block types. And different block types have different levels of importance. For example, super block might be more important than inode block, or inode block is more important than data block. Okay? And the second fact is, again, different volumes usually require different reliability levels. If you have an archival volume, usually you want more protections than a temporary volume. So what we need here is the ability to specify fine-grained policies. And we can achieve that with the policy table. So the first benefit of policy table is we can deploy different policies for different block types. So for example here, if we see a write to if the shepherd sees a write to the super block, we just say we want to execute this triple mirroring code, which will add mirroring to the super block. But for inode or inode bitmap block, we say that we want to add checksum and parity. For data, we do not want to add redundancy, so we just do a simple retry. Okay? The second benefit is that we allow file system administrators to to construct different policy tables for different volumes. Again, for an archival volume, you can have policy table that employs more protections than the policy table used in a temporary volume. Okay? So the second question in building this architecture is how we can write simple but powerful policies. But in short, basically, we provide lots of primitives that are very usable across different policies. The whole idea is that we try to hide complexities of handling these failures behind these primitives. And since that's the case, then the job of the policy writer, like the file system administrators, is just to compose these primitives into a fully formed policy code. Okay, so the policy code in general should be very simple.
Is it custom language or code?
No, it's C code basically, but it's just simplified. Okay. All right, so let's put it all together. So normally, if you have a request, you just directly send this to the storage subsystems. With Shepherd, we can modify the request or add more IOs to add the reliability. So for example, if we see a write to data block D, we can specify a policy table that will say that for data block, we want to mirror the data. So every time you see a write to data block, it will call this policy code. And the policy code should be simple. It just calls a bunch of primitives. So for example, it will look up the mirror map that is provided by the Shepherd. So the mirror, let's say this is a new data block. There is no replica yet. So the policy code will call another primitive to the file systems asking for a new block for the replica block. And then it will update the mirror map such that indicating that D is mirrored to R. And we can write the code that sends these two blocks to the disk.
Is map allocate actually an ext3 function within the file system?
The mirror map?
Yeah, the map allocate function. Like, are you calling?
No, this one is calling back to the file systems because we must always adhere to the.
So the Shepherd is linked into the file system.
Yep, correct. Inserted in for some functionalities. Yep. And the mirror map will be updated by a background primitive. So the whole point is that we can interpose IOs and we can add reliability in a very simple way. Okay. So in terms of implementation, the Shepherd infrastructure is around 3,500 lines of code, and much of this code is reusable for other file systems. Some of this code is very much integrated with the file systems, like the block types, allocations, and everything. And in terms of integrations to the operating systems, I need to modify ext3, but so far the modification is just 900 lines of code. But I want just to emphasize the most challenging integrations, which is integrating the IO shepherding with this consistency management in the ext3, in this case, the journaling layer. And my apology, I cannot show the problem because it needs 30 to 45 minutes to establish the problem and the solution. But the whole point is that the Shepherd adds new data and metadata to add reliability. And those additional data and metadata needs to be consistent in the presence of crashes. So when I want to integrate that to the journaling, I found that there's a major flaw in the journaling layer such that it cannot react to the checkpoint failures. And I can talk about that offline. But the whole point is that due to this major flaw, that's why you see that all write failures are being ignored in ext3, IBM JFS, and Riser FS2. That's because of this major flaw.
So is the flaw present even without your IO shepherding implementation?
The flaw, if I want to formally define the flaw, is that when we look at individual block failures, the journaling cannot handle that. The journaling layer only handles consistency in the presence of crashes. But when basically the whole point with journaling, you put your blocks in the journal area first, and then you checkpoint it to the final locations. When you checkpoint this to the final locations, the current journaling layer says that you cannot change the transaction has been committed there. So if you want to do remapping or mirroring or something like that, where you change the metadata that has been committed to the transaction, is too late.
So Your answer, this flaw shows up anytime you try to extend the file system with new features. Is that right?
No, even let's say that, let's just not talk IO shepherding. Let's just you want to add remapping policy in the ext3 file system. You cannot do that. Okay. You cannot do that and achieve consistency in the presence of crashes because of this major flow.
Journaling in file systems is pretty much analogous to logging the databases. So do you have any idea what the commercial databases do when they see write failures when they're trying to do installs?
No. So in database, they have this idea like compensating transactions. So I mean, the whole idea with database, they kind of log like the old data also along with the new data. But in terms of dealing with individual block failures, I haven't really looked into how database management systems handle.
Compensating transactions are for dealing with forts and things
Right.
that are higher level rather than a medium
Right.
failure. But they must have faced this problem because it's exactly the same problem.
And you've sort of already decided to commit the transaction.
You've committed the transaction, right? You've got the commit record in the log, and the check pointer is running along trying to install stuff from the log into the volume, and it's easy. I mean, maybe it just blows the volume, but it's harsh.
Maybe it pops up a message, buy a better disk.
Well, I mean, yeah, we have the moral equivalent, and you get delayed write back failed, right, which is not very helpful. But
I think the whole neat idea about this is that when we think about individual block failures coming into the picture, and we look at how today's systems try to handle that, it's not really complete in the sense this way. Yeah, I don't know. I cannot.
Usually they're ahead of us, so.
yeah. So one of the novel contributions that I've added this whole idea of chain transactions, and I can talk that more offline.
This word non-intrusive. How do you define that?
I'm sorry?
Non-intrusive there. How do you define that?
Pretty much it's like it's simple changes. Like for example, the shepherd needs to call back to the file systems and giving new block to.
How many files were those 900 lines changed in? Was it like 5 lines in every file, or was it like mostly all in a couple places?
No, mostly in localized. Like for example, allocation policies. The reason why I need to introduce more because the original file system code is so messy such that I cannot reuse the original file system code. I need to take some part of the code and write this new code. Yep.
I was
part of this is the consistency.
Trying to mentally add up the sizes of all the files in the ext3 that you had, and I came up with about 10,000. Is that how big it is?
ext3 file system?
That was
20,000.
Okay, so up by factor.
Yeah.
Factor of 2. Okay, so you're still adding.
Yeah. Well, I mean, part of this is this new solution chain transaction, right? And it's just one of the things that I must do to preserve consistency.
20,000 include the JBD file?
Yep. Okay. The whole ext3.
So can you add chain transactions to the original file system without having IO shepherding? Is that, because it seems like it's
Yeah, you can. Yep. All right, so let's evaluate IO shepherding briefly here. So I've shown you how we can achieve flexibility, fine-grained policies, and simplicity. So the whole point, again, this is the original ext3 recovery policies that can be summarized in this picture. So let's say we want to throw away all these policies, and let's say we want to add a simple retry more policies. We just install a policy table that looks like this. If you see a read to any block type, it will call this policy code. It will read the block, and if it keeps failing, it will retries. And if the retries keep failing, it will just returns to the failure. Okay. So I ran all the workload again, inject the faults again, and basically, as you can see, we can have a different kind of a recovery model. Okay. And we show you how we can do fine-grained policies. So let's say we want to change ext3 write recovery policies to custom policies, like a combination of different policies depending on the block types. But the takeaway point again here is kind of the overall behavior. You can just focus on the color. If it sees a write failures on the data blocks, it will do as what I tell in the policy table, which is retry and propagate, and the same thing for journal and metadata block. Okay. And writing reliability policies overall simple. And so far we have I've just written 8 policies, and the most complex one can be written in 80 lines of code. Okay. All right, so let me just briefly describe. Yes.
Could you talk a little bit about how this is philosophically different from something like software RAID, where I would explicitly try to do something like, doing something like mirroring in software, right, at the block level has been done before. So,
right. Well, it goes back to that slide that I kind of skim a little bit fast. Is that there are lots of techniques out there, right, and lots of techniques not about rate. Sometimes you want to do checksum, and sometimes you want to do parental checksum. Like you want to put the checksum not next to the block, but like in other different area, right? Sometimes you want to do like read after write, just to make sure that your writes are not lost. So basically the point is that there are kind of different kind of policies, and the Shepherd just allow that you deploy that kind of policies.
Okay, but is one of your other research results that a better software architecture is to put all of these within the block level rather than scatter them throughout the file system level?
Yeah.
To move many of these policies that you found scattered throughout.
Yeah, policies that deal with block level failure.
They need to go lower down? Okay, and this was not being done in something like the ext3 file system?
Yep, no.
So, also philosophically, how is this different from aspect-oriented programming, where you have a set of aspects that you're going to weave into code? It looks like you're refactoring the recovery aspects out of the code.
Yeah, good questions. Honestly, I haven't really explored it. What I've read is one title that there are some researchers that mention that AOP doesn't work for failure handling, and I've talked to some PL professor at Northwestern. He says that when you do AOP, there are too many. When you talk about fault handling and aspect-oriented, there are too many cross-cutting concerns. But yeah, to be honest, I don't know about all the details. But people that have looked into AOP and failure handling, they say that they do not really kind of match. Okay. But yeah, I love to talk about that later if you want. Okay. All right, so I will not give you too many technical details. Again, I just have a kind of lovely pictures that I want to show, so you can just sit back and relax. So let me show you the first one, which is static analysis of error propagation. So the problem definition is simple. You want to do one operations, you call a bunch of functions. These functions will call a bunch of other functions as well. And if there are low-level failures, error code such as EIO, that stands for IO error-related code, will be propagated. And this error code must be propagated as long as the error has not been handled, or as long as there's no print case statement, for example. At least you should not have silent failures. But as you can see, these do's and calls basically ignored all the written error codes that are written by the screen functions. Okay? So this is what we call as bad calls, because failures are being ignored. So even though there are some failures, the do's and call always return success to the caller, okay, which is bad. So we want to understand the magnitude of this problem. I wrote a static analysis, but here's kind of the result in the ext file systems. So all these nodes represents functions, all the edges represents function calls, and error code propagates upward. And all the function and function calls appear in this graph are those that are just touched by the error code. So in reality, there are many more functions and function calls. Okay? So you can just focus on the red edges because those are the places where failures are being ignored. So here's Ricer IFS, pretty much 35 places where failures are ignored. IBM JFS, 61, NFS client, 54, and behold, SGXFS, 105 places. Okay? And this is the most complex Linux file systems. Okay, so when I did a more thorough analysis, basically what I found, this is not corner case bugs. There's somewhat a pattern. For example, write failures are ignored many more than read failures. Okay, so I believe this is another hint of design, kind of reliability design issues in the today file systems. Maybe it's hard to recover from failure. Maybe it's hard to roll back in the middle of operations. And you can look at the developer comments that I will show you later that kind of hinted all these problems. So many questions that are still to be answered in this particular research.
So why is it bad to have more red?
Because you have silent failures. So there are failures, but the failures are not handled, and it's not even printed.
So, but how do you know it's not just fault tolerant? I mean, you could have tolerated failure.
Yeah, for some, I mean, from the file system research, goes back to the file system research, we see that write failures are really being ignored. When we look at the I/O operations under the file system, we do not see any more I/O. So it means that write fails. Oops, too bad. Yeah. Okay. All right. So, and also I've done a little bit work on database DBMS and data corruptions. The whole idea that the file system is not the only system that manages data in the storage subsystems. DBMS also stores its own internal metadata structures. So basically, we injected corruptions to MySQL on these data structures, and we want to see whether MySQL could tolerate such failures. And turns out that the results are damaging. The server crashes. Sometimes wrong results are written to users, which leads to security problem. Sometimes records are lost. And I think the more ridiculous part is that MySQL also has a repair utility. And this repair utility ignores the crop metadata, but sometimes it even trusts the crop metadata, such that it also crashes when it wants to do the repair. Okay, so.
Databases? MySQL's kind of an academic tool.
What I've done is just MySQL and Postgres. Postgres almost pretty much have the same problem. Well, Jeff Norton said that they.
Yeah, no, IBM's bites.
Yeah, I mean it's
therefore it's commercial. Well, therefore you should look at DB2. Yeah. Right, because now it's been subsumed.
Yeah. Jeff Norton actually told me that he can run this on DB2, but he cannot tell me the result anyway. So.
Yeah. The license agreement might stop you. Just
okay.
Obnoxious.
Again, I've done some work on deconstructing kind of real production AMC storage cluster. The whole idea that I developed techniques to unearth internal protocols and policies without looking any single lines of source code, and there are many benefits that we can do from the results. I've also done a little bit work on deploying network services in user level. So the whole point is that there are lots of TCP innovations out there, but you must convince the operating system developers to deploy your TCP in the kernel. So the questions for us is how we can expose information and save control to the application so that we can deploy these network services at the user level. Okay, I love to talk this offline if you want. Okay, let me just conclude with summary and future work. So I'm going to show you some comments that I found in kind of problematic cases in file system. So ext3 developers wrote, there's no way of reporting error to user space, so let's just ignore it. XFS, just ignore errors at this point. There's nothing we can do anyway except to try to keep going. Sifs, should we pass any errors back? Yes. SCSI to do, I think we need to handle failure. Okay, so I think the whole point is that there are many reliability problems in today's file systems, even the storage drivers. So that's why my roadmap is about the need to measure reliability first and to build powerful, reliable file systems with simplicity in its design. And what I've done in pretty much in one sentence is to make today's file systems, including the offline file system checkers, more reliable by kind of removing unnecessary complexities in its design, but without sacrificing power and performance. So again, with offline file system checker, I've shown you how we can simplify the constructions of file system checkers with the use of declarative query language. And for file systems, how we can simplify the reliability management with the shepherding layer. Okay? So in terms of my future work, my vision is twofold. The first one is to build highly reliable systems, and I believe there are three important requirements. The first one, I believe that failure management should be revisited. I found major flaw in today's journaling file systems. I still found flaws in error code propagations in today's file systems, and there are still many questions to be answered. And when I talk to some systems developers, they admit that some of these problems that they are aware of, but it seems that they just let it go. They do not have kind of a real solution. So at least from my part, there are lots of results that I can use as a database of problems to unearth as many design issues in file system reliability. Well, the second research is about simplifying systems, because I just believe that tomorrow's systems will be much more complex and much more larger than today's systems. And if we keep writing this large and important software in a low-level approach, it might be hard to manage the failures. So it's a kind of a great challenge to come up with a high-level approach to describe how large systems should operate. And maybe if we can come up with a good high-level approach, maybe again we can verify and formalize the reliability of these large systems. Okay? And the second vision is to build highly available systems. And simply, I believe that reliability cannot stand alone. If you have reliable systems but low availability or low performance, most people will not use that. And that's the lesson I learned from the storage industry, is that there's one case where they need to take off the file systems for 4 hours just to cross-check petabytes of data, and the users are really mad. So there are many works that can be done in this area. One kind of a short-term project is how we can build a fast online repair as part of the file system itself, so removing the need of offline checker. Okay? Let me just briefly describe the scope of my future work. I love to work with cross-disciplinary areas. So in my research, you have seen how I steal ideas from other areas, such as software engineering and databases. Again, I always love to evaluate large critical systems beyond file systems. I've done a little bit work on DBMS. It will be interesting to see other systems like distributed systems, cloud computing as well. And again, I really look forward to see my opportunity in evaluating these new trends. Solid-state drives is one example. I want to look at how systems built on top of these new drives. And it's just fascinating that today's system is not just about one machine or one operating system. So again, I also look the opportunity to look into how I will evaluate cloud computing. Okay, so let me just conclude with this quote from Tony Hoare. He said that the unavoidable price of reliability is simplicity, but it doesn't mean that today we should remove the features that we have in today's systems. But so we must accept that tomorrow's systems will have more features. It will be more larger than today's systems. So that's why in my research, I basically try to solve this new challenge, is how to build large, reliable systems with simplicity in its design. Okay, so that's it. I'll take more questions now. Yeah.
I'd like to return to the question about how common partial failures are.
Okay.
And so did those measurement studies that you talked about at the beginning of the talk document that partial failures are more common than full disk failures?
You mean intermittent failures?
It means like latent sector errors or restricted writes.
Well, or whatever class of partial errors is relevant to this talk, right? Either intermittent failures or corrupted data, like either things that get fixed by retry or things that, were data corruption on the disk.
Yep. The whole story that it happens, and it depends on turns out it depends on the storage drives also. If you buy a SATA drive, which is more cheaper, turns out they find that they have more partial failures than SCSI drives. And depending on the kind of like infant mortality, if you deploy your drives within the first or 2 years, sometimes you see more partial failures than if the disk has been around for 3 or 4 years. And there's also like correlation that sometimes if you see a latent sector failures, usually you'll find more sector failures in that disk because overall the disk is just gone bad, right? So that things just happen.
But how does it compare
to hold this?
Times that the entire disk
right.
becomes unavailable?
So I can look at the numbers, but so far I don't have the numbers on top of my head. But the whole thing from the storage industry is that when they look at these things, they need to build kind of new stuff to deal with these partial failures. Mm-hmm.
Full disk failures are more common, but not enough more common that you can ignore these things. These problems are real, serious problems.
I guess
I'm going to preface my question. I don't understand much about file systems, and it's kind of hard to argue with the thesis of your work that simplicity is desirable. I'm trying to understand what is unique about file systems, and people have tried to make other systems simple as well, and there's similar approaches of using declarative query languages and pulling out policy pieces in independent components. What do you think is what do you think the unique challenges are there in a file system versus other systems that have tried such approaches?
The most challenging part is it's stateful. What you store on the disk is non-volatile. If you look compared to networking has done a great job in dealing with kind of fault management and everything. You lose packets on the fly. But if you look at network, I can argue that pretty much you send packets, and if it doesn't come back, you try more basically. But if you look at file systems, you store data. Maybe you do not look at data for 1 more year, but 1 year after now, you expect the data to be still there on the disk, right? So that's, I think, the most kind of the unique challenge in file systems, because the whole idea that this is kind of stateful system.
But in P2P network, you also have a state.
Right. So agree. So when we look at P2P, then the file systems reliability research comes into that picture. Yep.
It's in the file system, not the network.
So as we move towards cloud-based storage, we're trusting our data to some service provider, and there are service level requirements in place that says, okay, I'll guarantee a certain availability of the data. So in that context, do you think file system reliability is still as much an issue for the end user? Because I can just outsource my data or give it to this service provider and not have to worry about these failures.
So let me please let me know if I get this correct or not. But even when we talk about cloud computing, one of the challenging parts in cloud computing today, stated by Yahoo Cloud architects and many other architects, is data management, right? How do you deal with failures at a large scale? And nobody have looked into failures at a large scale as large as cloud computing framework. Right? People, what we look is single drive failures and everything. So when we look at large scale failures, and the whole principle of reliability comes into the picture also, how we should deal with replication, data management in such a large scale failures. But from end user, I agree. There will be at the end is kind of a certain reliability guarantee that the infrastructure provides. And the user, usually users are lazy in the sense that you do not want to add these details to the users. So it will be, what my research is about giving more power to these infrastructure developers to build more flexible and more powerful policies.
I want to follow up on these kind of little questions in the sense, I'm also not an expert in file systems, but it seems to me like the technology, the disk basically has been around for a long time, and people looked at reliability 10 years ago, and I don't have a sense that this somehow are less reliable today than they used to be. And my question is kind of on the opposite, which is, do you think like we're going to be working on reliability for the disks 10 years from now? Like, are we making progress on this problem, or is what's?
Well, I think the story, if you look at the disk, for example, the density of the disk become more compact, right? You have like lots of bits per square inch of your drive. And if you look at some articles, they mention that when you want to build firmware on those particular drives, it's very hard, it's very complex, because you deal with very tiny little things. So that's why that kind of bug comes in. When you have more complex hardware to deal with, usually the firmware is not as perfect as what you want. That's why, originally it's just anecdote, but if you look at articles starting like 3 years ago, people say how this drive firmware can be buggy, such that your writes are lost. That's not just because of the media itself, but because of the firmware. So it really depends on the technology, on the full storage subsystems. It's not just the hardware itself.
It's actually tragic, because we didn't understand how disk failed until the last 5 years, because nobody had 100,000 disks sitting around to study, to see how these failures propagated themselves. Your disk has 1 million lines of source code in its firmware, and they just keep stuffing more functionality into it because the chips keep getting bigger. So they're right.
And so the short answer is nobody looked 10 years ago to see if disks were doing stuff like this. So we don't know the answer to your question, but there's anecdotal evidence of databases finding torn writes and other behaviors that couldn't be explained by a correctly functioning stack. So maybe the disks were broken back then, and maybe it was the software in the database, and probably it was all of the above.
It seems like if everything else keeps getting more reliable, then disks will become more and more the less reliable thing. They become the longest pole in the tent over time. So you sort of have to keep up with the rest of the stack.
So I have a question, which is kind of building on some other people asked, which is lack of error handling or inappropriate handling of errors is a common problem to, I assert, every code base, not just disk code base. What have you learned that could be reused? So let's say you decided tomorrow you were going to start looking at compilers or kernels or device drivers. What have you learned that's reusable? Or is everything you learned is everything you figured out, all the tricks that you figured out, are they specific to disks?
I guess the tricks, yes, but the principle again is very, very much extended. Just take one example for cloud computing. Okay, there's this work by Joe Volker from UCSD, and he mentioned that if you look at the this thin cloud computing software, if you look at the code, the service management part and the data management part is very cluttered. So if you want to express different kind of policies for different kind of data management, you cannot do that in that particular software. Right? So what they do is they kind of decouple those two, and how do you decouple those two will be very much technical to the problems that you want to solve. So pretty much I would say that the principle can be extended, but the details, I believe you just need to find your own tricks. Yeah. Mm-hmm.
All right, great. Thanks, Steve.
All right, thank you.